Welcome, ladies and gentlemen, to this video tutorial. Let's take a look at the following question. So here we've got a function big F defined as an integral of little f, where little f is given as the following piecewise function. So let's take a look at question A. Show that f is not differentiable at 0 and explain why this does not contradict theorem 4.3.4. Okay, so before we start, let's just take a look at little f. So let's take a look at the graph of little f. So when t is not positive, our function is this affine function t minus 1. So the graph looks something like that. And when t is positive, then the graph of little f looks something like that. So notice here this jump discontinuity here at 0. And that is what we will use to show that big F is not differentiable at 0. So remember, big F is differentiable at 0 if the following limit exists. So the limit as h tends to 0 of big F0 plus h, why 0? Because we're trying to work out the derivative of big F at 0. So that's why we have a 0 there, minus, whoops, that is not h, that is 0 all over h. Okay, so we will show that this limit does not exist. And how will we do that? Well, we will do that by showing that the left limit and the right limit of this limit does not exist. So let us consider the right limit. So let us consider the limit as h tends to 0 from the right of big F 0 plus h minus big F of 0 all over h. Okay, and so that is the integral from 0 to h of little f, but since h is approaching 0 from the right, this value that we are substituting into big F is positive. And for positive values, little f takes on the value 1. So this is going to be the integral of 1 dt minus the integral from 0 to 0 of little f t dt. But this is the integral over an integral of over an interval of 0 width. So that is going to be equal to 0. So let us see. This is the limit as h tends to 0 from the right. That integral is h over h, which is equal to 1. So h over h, everything cancels, and that is equal to 1. So this limit is equal to 1. And let us consider the other limit, so the left limit. So the limit as h tends to 0 from the left of big F 0 plus h minus f 0 over h. And now remember, we're taking h as h tends to 0 from the left. So h tends to 0 from the left. So this, what we're substituting into f, is going to be negative. So the limit as h tends to 0 from the left is going to be, well, big F, how is it defined? That is the integral from 0 to h So that expression is the top bound for our integral, and when we plug in negative values for little f, we get t minus 1. So that is t minus 1 dt minus the integral from 0 to 0 of f, of little f t dt. And since we're integrating from 0 to 0, that term falls away. And don't forget r over f. So the limit as h tends to 0 from the left, that is t half t squared minus t, evaluated in between 0 and h, all over h. And what is that? That is the limit as h tends to 0 from the left, and that is a half h squared minus h over h. And that is, well, that is going to be a half h minus 1. And if h tends to 0 from the left, half of h is going to tend to 0. So this limit is equal to minus 1. So now we see that the left limit is equal to minus 1. The right limit is equal to plus 1. So therefore, this limit does not exist. So since Since 1 is not equal to minus 1, the limit does not exist. And hence, big F is not differentiable at 0. Okay, and the second part of the problem asks, why does this not contradict theorem 4.3.4? So theorem 4.3.4 is the fundamental theorem of calculus, which says if we define a function big F like this, then if we take the derivative is essentially going to be little f. However, that is under the condition that little f is continuous everywhere. So here, little f is not continuous because it has this discontinuity at 0. So, and therefore big F is not differentiable at 0. And why does that not contradict theorem 4.3.4? That is because little f is not continuous. It does not satisfy all the conditions of theorem 4.3.4. So since little f is not continuous everywhere, little f does not satisfy the conditions. To be able to apply theorem 4.3.4. So we cannot apply theorem 4.3.4. Let me just double check the numbering. Theorem 4.3.4. So we cannot apply theorem 4.3.4 to conclude that big F is differentiable everywhere. Because little f does not satisfy the conditions of that are required to be able to apply Theorem 4.3.4. So Theorem 4.3.4 says that if little f is continuous everywhere, then big F is differentiable everywhere. However, here we have a discontinuity in little f, so we cannot apply Theorem 4.3.4, and that is why this example does not contradict Theorem 4.3.4. Okay, let's take a look at part B. Determine all x at which big F is differentiable and find the derivative at these values of little x. Okay, so how can we do that? Well, we know exactly what little f is, so we can actually work out all the values of big F. So little f of t, this is part B, is defined as, what was it defined as? That is t minus 1 when t is less than 0 and 1 when t is greater than 0. Okay, so we can actually work out what f of x is. Well, when x is strictly less than 0, f of x is the integral from 0 to x of t minus 1 dt, and when x is greater than 0 is the integral from 0 to x of 1 dt, and when x is equal to 0, f of x is the integral of, well, notice here, when t is less than or equal to 0, this is the integral from 0 to 0 of t minus 1 dt, but since we are integrating over an interval of 0 width, this case reduces to 0. And it's not too difficult to see that this reduces to just x, and this, if we do the integral, becomes half x squared minus x. So this is exactly what the values of f takes on. So now we can actually think about what the graph of f looks like. If we think about this quadratic, if we squint a little bit, this has let's see, where does it have zeros? It has zeros at, if we factor out an x, half x minus 1. So this quadratic has a root at 0 and at 2, looks like. So to the left of 0, what does the graph of big F look like? It looks like a quadratic that has a root at 0 and at 2. So, but we're only looking at the left part, or the part where x is less than 0. When x is equal to 0, the value of big F is 0, and if x is positive, then the value of big F is just x. So we see here, what does the graph of big F look like? It looks like a parabola to the left of 0 and a straight line to the right of 0. And notice this little cusp here at 0, which confirms what we had before, that big F is not differentiable at 0. And this allows us to write down all the points where x is actually differentiable. So if we take any point to the left, and we restrict our view just to this part of f, then everything looks like the quadratic, and the quadratic is nicely differentiable. So for x less than 0, f is differentiable at x, and the derivative of f at x is equal to what? X minus 1. And for x greater than 0, f is differentiable at x, and we've got the derivative of f at x. So for x greater than 0, f takes on the value x, so the derivative is just equal to 1. So where is big F differentiable? It is differentiable everywhere except at 0. Okay, let's take a look at part C of this question. So we want to show that f is continuous everywhere on R. So in part B, we've already shown that f is differentiable everywhere except at 0. So that means, since differentiability implies continuity, f is, we already know that f is continuous everywhere except at 0. We don't know yet at 0. So since big F is differentiable, for all, and I'm going to write it this way, x, or let's say at all x in R without 0, f is continuous at all x in R without 0. Okay, so we only need to check at 0. So we only need to check if f is continuous at 0. Okay, so let us check that f is continuous at 0. So let me reiterate how what we know about f. So we can write f as the following function, and we only need to check that f is continuous at 0. So we need to check that the limit as x tends to 0 of big F of x is equal to the value at 0. And the value of f at 0, that is equal to 0. Okay, so how will we check this? Well, look at big F. It is piecewise defined to the left and to the right of 0. And remember, there is a theorem in chapter 3 that says the limit exists if and only if the left limit and the right limit exists, and the values of the left and right limits are equal. So let us consider the left limit. So as x tends to 0 from the left of big F of x, what is that? That is the limit as x tends to 0 from the left of, and when x is negative or to the left of 0, that is a half x squared minus x, which, and this is just a polynomial. Polynomials are continuous, so this is just substituting 0 in 2. into x there. So that is equal to 0, which is equal to the function value of big F at 0. And let's consider the right limit. So the limit as x tends to 0 from the right of big F of x. What is that? That is the limit as x tends to 0 from the right of x. So to the right of 0, x, big F takes on the value x. And that is just equal to 0, which is f of 0. So therefore, the limit as x tends to 0 of big F of x is equal to 0, but that is equal to the function value of big F at 0. So when x takes on the value 0, big F takes on the value 0. And hence, f is continuous also at 0. So we conclude that big F is continuous on all of R. Okay, that is it for this one. I will see you in the next one.